This section is about automatic machine learning for the recommender system. Recently, the deeper recommender system, they have attracted a lot of attention from both the industry and the research communities because they have two advantages. One is they have strong ability to represent the features of users and items. And the second is they are good at modeling the nonlinear relationship between users and items. So typically, the deep recommender system contains three parts: the embedding layer, the interaction layer, and the inference layer. So the embedding layer transforms the users and the item features into the low-dimensional embedding vectors, and then we capture the relationship between the two features by the interaction layers, and finally they are passed through the inference layer to calculate the prediction result. So, however, most existing deep recommender systems are based on the manually designed architectures, but this requires a lot of expert knowledge of deep learning and the recommender systems, and it also takes a lot of time and engineering effort, and also sometimes the human mistake and the bias could lead to the suboptimal architectures. So why we believe AutoML can somehow address these challenges? So AutoML allow you to provide the labeled training data, the metric you want to optimize, and some constraint as the input, and you will directly receive the optimized model as output. So if we introduce AutoML for deep recommender system, their architectures are designed by the machine automatically. So this requires less expert knowledge, and it saves a lot of time and human effort. And if we input different data, the output architecture is different. For example, the news recommendations and the video recommendations, because they use different data, they have different features, so they will have different architectures. So in journals, there are two groups of AutoML methods for neural network architecture search. So one is RL-based method. So the high-level idea is to introduce a controller network, which learn to select the optimal component from a large candidate set. So we can predefine some candidate components, such as these components for in the computer version, the CNN models. So, and the RL-based AutoML has two parts. So one is the controller, which learn to find the more promising component. And the other part is the child architecture. So this is the deep recommender system with a particular architecture. So the components of the child architecture are sampled by the controller. So the child architecture may be different each time. So the process is that, so given the candidate component, we will sample, for example, there are only 3 candidate components. We will sample one component by the controller, and then the model, and then we get a model with a specific component. And then we update the model parameters by minimizing the training loss. And we will also evaluate the model on the validation set, and we use the model performance on the validation set as a reward, and we use this reward to update the RL-based controller. So this is the RL-based neural network architecture search model. And the second group of AutoML methods are the gradient descent-based methods. So the algorithm is based on the continuous relation and the gradient descent in the architecture space. So to be specific, given the predefined candidate components, and we will weighted sum the output of 3 candidate components according to the controller's weights, and then we get a model. And then we update the model parameters by minimizing the training loss. And for the controller, we can directly update the controller parameters by minimizing the validation loss. So these are the two well-known AutoML methods for the neural architecture search. So we will introduce two sets of applications of AutoML in deep recommender systems. One is for the embedding layers, and another is for the interaction layers. So we will first introduce the applications in embedding layers. So in the real-world recommender systems, they usually contains hundreds of feature fields. These feature fields come from the users, items, contextual information, and their interactions. So as we mentioned before, the deep recommender system will transform these features into embedding vectors. So however, in most existing systems, they assign the same dimension, the same embedding dimension for all the features. So I think this way use the embedding memory inefficiently. So I think there are three reasons. So one is actually the embedding dimension often decides its ability to capture information. So if we simply assign the same dimension to all the feature fields, we may lose the information of important features, but waste the memory on the unimportant ones. So for example, the location feature is very important in the location-based recommender systems. So we should assign it with a large dimension. And another reason is actually the different feature fields have a different number of unique values. For example, the gender feature only have two, male and female, but the user ID feature contains millions of unique values. So basically, we should assign the large dimension to the field with more values, and then we can encode more information of them and capture their relationship with other features. And finally, different features have different frequencies. For example, in the game recommendations, probably the feature male, the feature value male appears much more frequently than the feature value female. So according to these three reasons, we should assign different dimension to the different feature fields. I will introduce four papers in this direction. And the first is neural input search for the large-scale recommendation models. So this paper introduced a multi-set embedding. So the observation and the intuition is that we don't necessarily need to have the large embedding set for all the items. We only need to have a large embedding set for the head items. So this is because these items appears frequently in the training data set, as we just mentioned before. So this means there will be more information to be captured. So we need a large dimension embedding set for these head items. And for the tail items, so definitely we should assign a small embedding size because there are less information to be captured. And then the multi-set setting are introduced for the embedding matrix. So in this example, we have three features, and each feature has the largest allowed embedding matrix. Its size is 10 million by 256. And we first need to sort the items according to their frequencies, and then we can cut the embedding matrix into the small pieces. And here we cut the embedding matrix into five chunks, horizontally and four chunks vertically. And the way to cut the embedding matrix could be predefined. And this model uses the reinforcement learning based AutoML method, and we have a main model that contains the largest allowed embedding set for each feature. And then in each iteration, the controller will sample embedding configs and receive a reward from the main model. And over the training process, the controller will sample many different types of embedding configs, and eventually the controller will convert to the config that generates the highest reward. Here, the reward is defined as the quality reward RQ minus lambda. Lambda is a hyperparameters and multiplied by the memory cost CM. So the quality reward is the metric to optimize for the main model, such as AUC for the ranking problems. And the memory cost is the measure of overall budget memory usage of the controller's choice. So given the reward function, the controller is trained using the A3C algorithm. And actually, one challenge of the first paper is it assumes the items frequency are pre-known and fixed. But actually, in the real world recommended systems, the items frequency are not pre-known and they are highly dynamic. So we propose the ESAPN model. So this model also has two parts. One is the deep recommender system, and another is a policy network, which can select the embedding sets. So given a user and an item, the policy network will decide the embedding size, and then we will go to the embedding table to find the corresponding embeddings, and then we feed these embeddings into the main model, the recommender system, deep recommender system model, and we predict the user's preference of the item, and we use the prediction, the difference of the prediction and the ground truth as the reward, and then we use reward to update the parameters of the policy network. Here I will introduce more details of the deep recommender systems. So it has the embedding layer and the inference layer. So for each user or each items, we will assign different dimension, a set of embeddings with different dimensions, such as 2, 4, 8. And because the first layer of the inference layer is the input is fixed, such as probably 16. So we need to transform the user and the item embeddings into the predefined dimension, such as 8. So according to our preliminary study, we found that for the co-starred user or items, a short embedding can perform better. So for all the new or new items or new users, their dimension starts from the minimal one, such as 2. And then we use a linear transformation method to transform the short embeddings to the long embeddings, such as 2 to 4, 4 to 8. So this is the deep recommendation model. And next, I will introduce the policy network. So this policy network is the agent, the RL agent, to dynamically decide the dimension size. And for users and for the items, we have separate policy networks. And the environment is the deep recommender system we just introduced, because we get the reward from this deep recommender system. So this is the environment. And for the state, we have two parts. One is the current frequency of the users or items. Another is the current embedding sets of a given user or the given items. And based on the state, the policy network will take two actions: enlarge or unchain. So the enlarge means it will enlarge or it will adjust the embedding set to the next level. For example, from 2 to 4 or from 4 to 8, only one step. But under the unchained means that we will keep the embedding sets. So the reward is the performance. The LU is the performance, the previous performance, and if the current performance or the previous losses. So if the current loss is smaller than the previous loss, the average, we will have a positive reward. Otherwise, we will have a negative reward. So to better understand our model, we draw the we do the experiment, and the x-axis is the frequency of users and items, and we have the frequency from 1 to 100, and we can find and the red curve is the performance of our model, and we can find that no matter for the low frequency or higher frequency, our model can outperform the other models. So this is the second paper. And the third paper is the field-aware embedding dimension search in the recommender systems. So as we mentioned, assign the different dimension for different features is complex. I think there are some reasons. The first challenge is the relation among the embedding dimensions, the feature directions, and the neural network architectures is very complex. So in the other words, they are highly depends on each other. So if we change one, the others will also change. So this makes it hard to manually adjust the embedding dimension separately. So this is about the first challenge. And another challenge is actually the real-world recommender system often contains hundreds of feature fields. So if we assign k candidate dimension to each field, then the total search space is m power of k. So this is a very large search space. So manually selecting from all the combinations is very expensive in both time and computations. So to address these two challenges, we propose an AutoML based model, AutoDIM. So our model can automatically select the embedding dimension to different feature fields. So this is the overview of our framework. We have two stages. So in the dimension search stage, we first assign a set of candidate dimensions to each feature field, and these candidates have different dimensions. And then we will unify all the candidate embeddings to the same dimension. Similarly, this is because we will feed the embedding into the MLP layers later, and the input dimension of MLP is predefined and fixed, so it cannot handle the various embedding dimensions. So we need to first unify the candidate embeddings. And finally, we weighted sum all the transformed embedding and feed them into the MLP layers. So here, the weighted sum probabilities are also trainable, and they measure the contributions of different candidate embeddings. And after the search model converges, we go to the parameter retraining stage. So according to the well-learned weights on the candidate embeddings, we can select the optimal embedding dimension for each feature field, and then we retrain the model parameters. So then, so this is our two-stage framework. And we found that our model achieved the best recommendation performance compared with the baselines, and at the same time, it can save 17 to 80% embedding parameters. So this result proved the effectiveness of our framework, and this framework has been launched in the some real-world applications in ByteDance. So this is the AutoDIM paper. It can automatically select the proper dimension for all the feature fields. And it can apply, this model can be applied to any deep recommender system with the embedding layers. And it can save embedding parameters, and it can improve the recommendation performance. And for the first three papers, we introduce the embeddings for the categorical features. But actually, in the real-world recommender system, we also have the continuous features. For example, in this case, the gender or the day they are the categorical field, and for the heat or the ages, they are the continuous values. So these are the numerical feature fields. So so for these continuous features, it's very hard to assign the embedding for different feature values, because there are a lot of the amount of the feature values are very large. So one traditional way is normalization. So in normalization for the continuous features, so all the numerical or the continuous features in the same field share a single embedding, and a scalar will multiply with the values. For example, we will multiply all these values with 0.1. But the disadvantage is that this method assume that the embeddings of different features in the same field are linear related to each others, and their contributions are also linear. But actually, in the real-world recommender system, probably their relations should not be linear. And another method is discretization. So this method partitions the range of feature values into k budget. For example, the age from 18 to 40, we consider it as teenage, and from 41 to 65, we consider it as the middle age. But actually, this discretization also have some disadvantage. First, they call it TPP. This means that this partition cannot be optimized together with the main model because these are handcraft. And the second disadvantage is the SBD. This disadvantage is that the different for the similar values such as 40 and 41, because they are they are set into the different bucket, so their embeddings can be very different, but actually their values are quite similar. And the third disadvantage is DBS, which means that for the very different values, such as 18 and 40, because they are set into the same budget, so they have the same embedding, but actually they are quite different. So this model, they propose a method to assign the embeddings for the continuous values. So they first assign a set of meta embedding for each feature field, such as heat or the age, and the number of the embedding vector is hg for the G's embedding field. And then given a specific feature value, such as age equals to 18, and we can calculate the probabilities over the embedding vectors by a controller network. And finally, the paper proposed 3 aggregation functions: max pooling, top k sum, and weighted average, to aggregate the meta embeddings. And then we can get the embedding of the features, such as the feature age equal to 18. So the advantage of this model is that first, this model is end-to-end, which means that the discretization of the numeric features can be optimized jointly with the main model. And also, the second advantage is continuous but different, which means that the different feature values are assigned different embeddings, but the closer feature values have the similar embeddings. So this is the 4 papers. I have introduced 4 papers for the embedding layers. And the next, I will introduce the applications of AutoML in the interaction layers. So because as I introduced before, the data in the recommender system is mostly in this multi-field form. So each field is a type of features. So here we give an example. It has 4 fields, and each field has many feature values. And from this form of data, the explicit feature interaction can significantly improve the model performance. For example, people like download popular apps. So here the ID of an app maybe the signal. And the people often download apps for food delivery at the mealtime. So here the interaction between the app category and the time step maybe the signals. So From this example, we can find that some interactions, some feature interactions, they can be easily understood, and then they can be designed by the expert, such as these examples. But in the real world recommender systems, most other feature interactions, they are hidden in the data and they are difficult to identify. For example, the diaper and the beer rule, and they can be manned by automatically by the machine learning models. So actually, factorization machine models, such as the FM, deep FM, it has been proposed to explore the implicit feature interactions. And these factorization models are widely used in many industrial recommender systems. But however, all these models, they are simply enumerating all the feature interactions, or they require the human effort to identify the important feature interactions. So the former one, enumerating all the feature interactions, they always brings a large memory and the computation cost to the model, and it's very difficult to attend to the higher order interactions. And the later one, the human identify the important feature interactions, and it's require a lot of engineering efforts, and it has a higher risk to missing some intuitive but important interactions. So here there are several papers trying to automatically find the important feature interactions. And the first is the auto FIS from the KDD last year. So this paper, they have two stages for the automatically selecting the feature interactions in the factorization models. So in the search stage, this selects the important feature interactions, and in the retraining stage, they retrain the model with the selected interactions. So how to search and detect the important feature interactions? So here, they set a gate for each feature interaction to control whether the output of the interaction will be passed into the next layer. So from a data-driven point of view, so whether open or close a gate depends on the contribution of each feature interactions to the final predictions. So this contributing so we should remove the interactions which contribute later. So the value of the gate are learned by the gradient descent based AutoML model method we introduced. And this table summarizes the performance by applying their model AutoFIS to the FM and the deep FM, and then we have auto FM and the auto deep FM. And we can observe that the AutoFIS, their model can remove about 60 to 80 the second order feature interactions, and the model, the recommendation model can achieve a better performance. For example, the auto FM compared with the pure FM, the auto deep FM compared with the original deep FM, they can achieve better performance. And the second paper is auto group, automatic feature grouping for the modeling implicit high order feature interactions in the CTR prediction. So the architecture mainly contains three parts: the auto grouping, the interaction, and the MLP. So this slide shows the auto grouping stage. This is the most important stage of the paper. So the purpose of the auto grouping stage is that for each group of interactions, we want to find some useful feature sets, such as we only need to model the feature interactions within the feature set. So take an example of the order P. Here they define the order P, and we have several groups for the feature set. And initially, each feature is possibly to select it into each feature field. And again, we have the two probability values. the selection or the non-selection. So if the selection is larger than the non-selection, then this feature is selected into a particular feature set, such as in this figure, the red line means means the selection. And once the feature set are determined, we compute the piece order interaction of the features in this feature field. And the model parameters are also learned by the gradient descent based AutoML method we introduced. So this is the auto group paper. So the advantage is that for each order of interactions, we can find some useful feature set, and we only need to model the feature interactions within the feature set. And next, I will introduce the last paper, Auto CTR, which also published in the KDD last year. So this paper first built a good search space, so which covered a lot of some good the human crafted structures, such as the MLP, the dot product, and the factorizations. And then we can build them together to form a deep recommender system. So an example is shown here in this figure. And first we group the input of the dense features and the sparse features into the two components, so that the features in each group are selected jointly. And the blocks can select to take both for both the raw input or the output from the other blocks, and the final layer will collect all the isolated features together to generate the final prediction. So the search space is the two-level search space containing both the block parameters and the connection among the blocks. And the author proposed a evolutionary search algorithm to learn these parameters jointly. More details, so please refer to their papers. In conclusion, the advantage of the AutoML for recommendation is that the deep architecture are designed by the machine automatically. So this can require less expert knowledge. It saves a lot of time and engineering effort. And for different data, we have different architectures. So for the future directions, so most current works, they focus on the architecture search for the neural networks. So actually, there are also other parts we can use AutoML to build a deep recommender system. So for example, when we do a regression task, such as the user state time prediction, we can use MSE and MAE loss functions. So the MSE is sensitive to the outer layers, and the MAE is not that sensitive, but its gradient is always the same, even for small loss values. So we can use AutoML to dynamically select the loss function for each data samples. So in the future, we can study more such applications of AutoML to build deep recommender systems, such as the feature engineer, the model selection, the optimization, and the evaluations.